Hello everyone and welcome back to the science class. In today's video, we will learn how to differentiate between heat and temperature. We will define specific heat capacity and we will learn how to calculate the amount of heat energy by using the formula Q equals mc delta T. Activity 1. Define temperature. On the screen, water is shown at different physical states: solid, liquid, and gas. Where do particles move faster, in solid, liquid, or gas? If your answer is particles move the fastest in gas, then you are correct. Particles in a gas move faster than particles in a liquid, and it's clear that particles move the slowest in solids. Right now, at which state temperature is higher? It's clear that temperature of water vapor is higher than the temperature of liquid water, and for sure the temperature of ice is the lowest. So, are you able to define temperature? Temperature is a measure of the average kinetic energy of the particles in an object. An increase in temperature reflects an increase in the particle's motion. Let's think together. Which one has more temperature? A cup of boiling water or a bucket of boiling water? In order to know the answer, let's do some math. If you made 5 quizzes and you got the full mark 20 out of 20 on each, what will be your marks average? In order to know, you'll add all the marks and you'll divide them by the number of the quizzes. In this case, the sum of all the marks is equal to 100. In order to find the average, you'll divide 100 by 5, which is equal to the number of the quizzes. So, the average will be 20. Suppose that right now you will write another 2 quizzes and still you got 20 out of 20. Does the average increase? For sure, no. Why? Because we are dividing by the total number of quizzes. Similarly, when we add more particles, the kinetic energy increases, but by finding the average, both a cup and a bucket of boiling water will have the same temperature. Accordingly, temperature doesn't increase with the number of particles. What is heat?
Welcome to What is Heat? Let's start with an illustration. Here we have hot and cold blocks of some material, and they each have a thermometer in them to prove the point. If we put them together, what's going to happen to the temperature of the cold block, and what's going to happen to the temperature of the hot block? Let's take a look. You can see that there has been a transfer of energy from the hot block to the cold block, resulting in the same temperature for each. Heat is a form of energy that flows from one object to another. What kind of energy? That's right, it's the flow of kinetic energy. And it is important to remember that the temperature is the average kinetic energy of a substance, in contrast with heat, which is the flow of kinetic energy. So what direction does heat flow? You're right, always from hot to cold. This is a basic fundamental law of the universe. But how does that happen? What is happening at the particle level? And another interesting question to ponder is, will there still be any heat flow now once the two blocks have reached the same temperature? We will address that question a bit later. So to understand heat, we need to understand how particles are involved in the flow of kinetic energy. Let's back up a bit. Starting with hot and cold again, let's see what's happening between the hot and cold blocks. We'll take a closer look using a magic bus. As we zoom in, you can begin to see the particles that make up the two blocks. The kinetic energy is shown as vibrational motion. The lower block in red has greater vibrational motion. It has a higher average kinetic energy and therefore a higher temperature. The upper block in blue has less vibrational motion. It has a lower temperature. What happens when a slow-moving particle hits a fast-moving particle? There's a transfer of kinetic energy. And how does that affect their temperature? Yes, the cooler particle becomes warm, the hot particle becomes cool. Let's look again as we put the blocks together so the surface particles are in contact. The collisions constantly transfer kinetic energy, which is depicted here with the particles becoming purple and reaching a more intermediate rate of vibration, or in other words, reaching the same temperature. Note they need to transfer kinetic energy both between and within each block for this to happen. Let's get back to a previous important question. Is there any heat transfer now once they have reached the same temperature? Think about it. The atoms are still constantly colliding and so are constantly transferring kinetic energy, but there is no net change in temperature. The two blocks have reached an equilibrium once they reach the same temperature. The amount of heat going from upper block to lower is equal to the amount of heat going from the lower block to the upper block. The rate of kinetic energy transfer between the blocks is now equal, which defines the equilibrium.
Activity 2. Define specific heat capacity. In order to understand the specific heat capacity, let's hear this story. Once upon a time, a block of copper weighing 1 kilogram, having temperature equals to 25 degrees Celsius, and would like to increase its temperature until 30 degrees. In order to do so, it must gain heat. So, he made an agreement with Mr. Oven in order to get the necessary heat to increase its temperature. Mr. Oven said, in order to increase your temperature 1 degree Celsius, you must get 385 joules. The block of copper made its calculation. From 25 till 30 degrees Celsius, the copper block has to gain 5 extra degrees. In order to increase the temperature 1 degree, 385 joules is needed. So, increasing the temperature 5 degrees needs 5 times 385, and then 1925 joules are needed. Another block of copper weighing 2 kilograms heard about this agreement and bought 1925 joules, but its temperature increased just 2.5 degrees Celsius. Why? 1925 joules increases the temperature of the block first by 5 degrees Celsius, while the same amount of heat increases the second block by 2.5 degrees only. Mr. Owen answered, 385 joules is the amount of heat needed to increase the temperature of 1 kilogram of copper by 1 degree Celsius. As your mass doubles, you need a double amount of heat. This table shows clearly that each material has its own specific heat capacity. If we have 1 kilograms of each of aluminum, silver, and gold, which substance need less heat in order to increase its temperature by 1 degree? The specific heat of gold is the lowest, which means that less heat is needed in order to increase the temperature of 1 kilograms of gold by 1 degree Celsius. In order to calculate the amount of heat needed by certain material to increase its temperature for specific degrees, scientists use this formula Q equals mc delta T, where Q stands for heat energy, m equals the mass, and delta T equals the change in the temperature, which is final temperature minus initial temperature. So guys, don't worry, you will find it very easy when we will apply what we learned. How many joules of heat are needed to raise the temperature of 10 grams of aluminum from 22 degrees Celsius to 55 degrees Celsius if the specific heat of aluminum is 0.90 joules per grams degrees Celsius? Reading the unit of specific heat is crucial in order to solve this problem. 0.90 joules per grams degree Celsius means zero point 0.9 joules is needed in order to increase 1 gram of aluminum by 1 degree Celsius. What is the value of the M? According to the given, the mass is equal to 10 grams. Will I change it into kilograms? The unit of mass is always set according to the unit shown in specific heat capacity. In this case, it's joules per grams degree Celsius. So I'm gonna keep the mass in grams. How many degrees do we need to increase the temperature of the aluminum? In order to know, we'll calculate delta T, which is T final minus T initial. In this case, delta T equals 55 minus 22. It will be equal to 33 degrees Celsius. Let's start first by writing the formula, which is Q equals mc delta T. Now we replace each term by its value. In the place of m, I'll write 10. In the place of c, I'll write 0.9. And instead of delta T, I'm going to write 33 as it's calculated before. As it's set in the formula, we have to multiply these terms by each other. So the final answer will be 297. What is the unit? The unit is joules.